Hello students, so welcome to part 4 of the lecture series on previous year gate questions of electronics and communication, and the topic is sinusoidal steady state response. We have already completed 3 parts and this is the 4th part of the lecture series. The lecture series is brought to you by EDAMIGO team. So let's start with the question. So this is the previous year gate question of electronics and communication. Here it is given that this is the input source, these are the circuit elements connected as shown in the figure. So we have to find the value of C so that the current through 50 ohm resistance is 0. Okay, so the important part is the current will be 0 when the impedance seen by the signal source or this voltage source is equals to infinity. So impedance seen by the signal or voltage source is infinity. So this is the requirement, then only current will be 0, then only this current will be 0. And since we can see that this is 50, this is j omega L, this is j omega L, this is j omega L, and this is 1 upon j omega C. So impedance should be infinity. Now I can say that since impedance is equals to the series combination of 50, this 50 ohm resistance, the inductance, and the equivalent of this whole combination. So the equivalent is actually the parallel combination of the inductance and the series combination of the inductance and capacitance. So this inductance and the series combination of inductance and capacitance, so all these two are in parallel and the resultant is in series with the inductance and resistance. So this is the impedance. Now this should be infinity. Now since this cannot be infinity, this cannot be infinity, now let's look at what is the third term. The third term is, so this is Z1, this is Z2, and the parallel combination of Z1 parallel Z2 is Z1 into Z2 upon Z1 plus Z2. So it is 50 plus j omega L. So it is j omega L multiplied by j omega L plus 1 upon j omega C divided by j omega L plus j omega L plus 1 upon j omega C. Now the impedance, this whole term will be equal to infinity when this denominator is equal to 0. Okay, so j omega L plus omega L minus 1 upon omega C should be 0. That is 2 omega L is equals to 1 upon omega C, and omega is equals to 1 upon under root 2 LC. Okay, or in other words, I can say that since we have to find the value of capacitance for the condition, so I can, and omega is given to us, that is 5000. So using this equation number 1, we have 2 into 5000 into what is the value of L? L is 1 millihenry. 1 into 10 to the power minus 3 is equals to 1 upon 5000 into C. So this will cancel out. This will give you 10 is equals to 1 upon 5000 into C. C is equals to 1 upon 5000 into 10. So this will come out to be 20 microfarad. Okay, so the value of C is 20 microfarad. Now a very important point is, since the value of capacitance is to be given in microfarad, so the answer is 20 directly. Okay, so this solves our question. Now let's move on to the another question. A very simple question. A very simple question. So it is given that we have to find the value of the peak output voltage. Now our output voltage is actually between this resistance. Now at very high frequency. Now what is the meaning of this? This is important. Okay. Now as we know that the impedance of the capacitance is 1 upon j omega c, and when omega is very high, then z tends to 0. That is capacitance act as short circuit. So in this circuit we have to apply this concept of, so this is the meaning of very high frequency that should be applied in the circuit. Now at very high frequency, since the capacitances are short circuited, so I can redraw the circuit, and it is 1 sine omega t. Capacitances are short circuited. 1 kilo ohm, 1 kilo ohm, capacitance short circuited, 1 kilo ohm and 1 kilo. So we can easily see that the output voltage is actually equals to 0.5 sine omega t, and the peak value of the output. Okay, so how do I get this output? By applying the voltage division rule between these two resistances. So between these two resistances, this and this resistance, so let us say this is R1 and this is R2. Okay, so by voltage division rule I get the output is equals to this. Now the peak value is 0.5. Okay, so this is the answer to the question. So it was a very simple question. Now another question. Okay, so first of all let's look at the circuit which is given to us. Okay, so it is given LC tank circuit which has an ideal capacitance connected in parallel with the coil having internal resistance of R. So I can say that the circuit is the parallel combination of a capacitance and a coil which has a finite resistance R and L. So this is your circuit. Now we have to find the resonant frequency. Now we all know what is the resonant frequency. So resonant frequency of a circuit is the value of omega at which impedance of the circuit is real value. Okay, so what should be the method? So the method to find the resonant frequency omega r is, first of all, to find Z equivalent of the circuit, then put imaginary part of Z equivalent is equals to 0 and find omega r. Okay, so this is we have to do. So first of all we will be finding the Z equivalent of the circuit, or one more thing that we can write here is the another method is, first step will be find Y equivalent. Y equivalent means the, so Z equivalent means the impedance and Y equivalent means the admittance, and put imaginary part of Y equivalent is equal to 0 to find omega r. So any of the method can be used. Since in this circuit the two elements are in parallel, so we can use the method of putting imaginary part of admittance equal to 0, so that will be a better method or an easier method. Okay, now since we have to find y equivalent between terminals A and B, so first of all I just remove this and replace it with the impedances. So j omega L is the impedance of inductance and 1 upon j omega C is the impedance of the capacitance. So y equivalent is equal to y1 plus y2, where y1 is the impedance, admittance of this capacitance, so that is equals to j omega C, and y2 is the admittance of this series combination, so it is equals to 1 upon impedance, so that is equals to 1 upon R plus j omega L. So y equivalent is equals to j omega C plus 1 upon R plus j omega L. So j omega C, so I multiply and divide by R minus j omega L, R plus j omega L multiplied by R minus j omega L. So j omega C, R minus j omega L. So the denominator will be R square plus omega square L square. Now, if I write the imaginary part of y equivalent, so that will be equals to omega C, because I will write it like this. So j omega C minus j omega L divided by R square plus omega square L square. So, this is y equivalent plus the term R upon R square plus R square plus omega square L square. Okay. Now the imaginary part is only this much. So imaginary part of y equivalent equals to 0 means omega C minus omega L upon R square plus omega square L square equals to 0. So from here we get that this implies that I will have to add a page, right? Okay. Now, so we can see that omega C equals to omega L upon R square plus omega square L square. Omega omega cancels out. R square plus omega square L square equals to L by C, and omega square is equals to L by C minus R. So omega is equals to 1 upon L under root of L by C minus R. So this is the result. Now, so to modify this, let us take, so here it is R square, okay, R square. So let us take L as common from inside, so we will get under root of 1 upon C minus R square upon L, 1 upon under root L. Now let us take under root C common from inside, so 1 upon root LC. So we are taking C as common, so 1 minus R square C upon L. So this is the result. This is the value of omega. So we can easily see that the result is, so you can easily see that the result is B is the correct answer. So B is the correct answer. Okay. So guys, thank you and stay tuned. We will be solving more questions on the same topic in the next part. Thank you.